Swayam Prabha. Digital India. Educated India.
We are talking about Markov chain to model physico-chemical processes. So in this class, I was thinking of doing two problems. One is looking at a reaction kinetics in a CSTR at steady state, and then also a fluidized bed reactor. Okay. So here I'll demonstrate how to apply Markov chain models in these two cases. What we hope to do here is we want to predict here what is the concentration in the reactor as a function of time. Our traditional approach to model CSTR is in a steady state, but here we can actually look at the transient of the CSTR and also reaching a steady state kind of behavior. So we can see the entire transient behavior. And in the case of fluidized bed, I will talk about what it means. So here again the idea here is to see what is the residence time, what is the average residence time for particles in the fluidized bed. Okay, so those are the things we can do. Both of them are actually traditionally modeled through deterministic or conventional models, but here we are given alternative description of modeling. So the first problem is let's say you have a reaction A going to B reversibly, right, with a rate constant K1 and K2. So you have a CSTR. Okay, you can say that the reactor volume is V, and you can say that the flow rate, okay, is Q. To keep things easy, we will keep a constant density, so same flow rate, steady state behavior. Okay, so in this case you have a reaction like this happening here. So our traditional approach, CRE reactor approach, is to write a design equation at a steady state something like this, right, where tau is V by Q, volume of the reactor divided by the volumetric flow rate. You get space time. Okay, Ca naught would be the initial concentration, and then you have conversion. You can write this in terms of Ca naught Ca, and this minus Re depends on this reaction kinetics. Okay, so this is how you kind of predict for a given tau, for a given stoichiometry of reaction, what is the conversion. Okay, or vice versa. You want to have a desired conversion. You have the reaction kinetics, rate constants, order, everything is known. You typically ask what is the volume of the reactor you need. Okay, these are the questions that we ask and answer in this case. Now, in the case of Markov chain, what we need to do is we know how to handle this kind of reaction scheme in a batch reactor. Okay, now when you have this kind of flow in and flow out, we need to model the incoming of reactant A and B, similarly the exiting of reactant A and B from the system. Okay, so now what we can do, I think we talked about this before in the context of chemical master equation. The input can be assumed to be like a zero order reaction. Okay, something like input, we say something like this. Okay, so input can be modeled as a zero order reaction with the rate constant, we say K I A, and not only A comes in, B may also come in. Okay, so we have another zero order reaction for K I B So here I means input, A means species A and B. Similarly, if you want to look at the exit, okay, so for the outlet, we think of this is like a decay process, right? A is getting removed, A is kind of reacting away into something else. For example, you can say A is going into some dead state because it's not going to come back to the system, it's gone, okay, it is like going out of the system. Similarly, B also decays. Okay, so just to distinguish, if you want to put this, is you can put like A, B, it doesn't matter, but if you want to be really careful about this, okay, so this is like a state created with IA, state created with IB, state destroyed with OA and OB. Okay, so here again you have constants like KOA, KOB, etc. Obviously, this KIA and KIB, those are actually related to the flow rate in and the feed concentration, like that. Similarly, this KOA and KOB, this must be related to the concentration and Q here. Okay, so we will relate that also. So as much as we know about the reaction rate constant K1 and K2, we also know how A is coming in, how A is going out, and how B is coming in and how B is going out. Okay, so essentially the CSTR problem can be mapped into a set of reactions. Apart from the chemical reaction, the inlet outlet condition also can be written in terms of a reactive scheme, okay, where the input is zero order reaction, because regardless of what is there in the system, you keep adding some constant rate. Whereas in this case, the outlet depends on what is the current concentration in the system is. So it's going to be more like a first order process. Okay, so now you got combination of all these things. So what we need to do then is write a set of equations in the deterministic format, integrate, set up the transition matrix, and then you write the Markov chain model. Okay, so that's what we are going to do. So we'll write for species A, so dCA by dt, you can put minus RA. So dCA by dt minus K1CA, this is a forward reaction, this is a backward reaction. This takes care of the chemical kinetics. Now we have two additional things, A is also getting created and A is also getting depleted. Okay, so I will say that this is equal to KIA because this is a zero order reaction, and then it is depleted with something like this, right? So if you want, you can write this as minus K1 plus KOA CA plus K2CB plus KIA. Now we will integrate this equation over a small time delta t. Again, time is discretized like before. So we have CA m plus 1 minus CA at m by delta t . So this is so now we can rearrange this. Now we do the same thing for species B. Oh, 1 minus. Okay. Yeah. Okay. So these are the two equation that we want to solve recursively for different m value or the type. So can you help me with the elements of the transition matrix? So what should be this, the first 1 minus delta t k1 plus koa, right? Okay, then this element is k2 delta t. How would I add this constant term? one more. So yeah, so we need to add a additional state to add a constant term. So what I'm going to do is I'm going to add a virtual state of unity. I'll add one here, and then here this becomes KIA delta T. Okay, so we create an artificial or virtual state so that this can be written in this matrix form. So this is a new information. You would have done this exactly this even for a batch reactor with a zero order reaction. Okay, and for this you would have K1 delta T one minus delta T into K2 plus KOB, right? Yeah, and then you have KIP. So therefore you can write C at m plus 1 is equal to C at m. So now I am writing in matrix form here. Okay, this is a vector and this is a vector. Yeah. Which dimension? Ah. Where? Okay. So you get 1 by 3 here, 3 by 3. So you'll get 1 by 3. Okay. Yeah, you're right. So actually I have to add one more column here. And that column, you're right. So it could be 0, 0, 1. Yeah. Zero, 0, 1. Yeah. Okay. So now let's qualify these constants based on the flow parameters. So in the CSTR, the flow rate is kept constant, Q volume per unit time, and the concentration in the feed for A is AF. F means feed, not final, feed. Okay, I'm using F not C and not CB not because sometimes we may have a starting condition. You can have some number of molecules in the system to start with also. So C and not CB not, we will use it for the initializing this. Okay, remember this corresponds to the concentration inside the reactor. So here I am talking about the concentration in the feed stream. This can be different from the initial condition which is present in the reactor. Okay, so the initial condition we will define as CA0 and CB0, or if you want to work with the number of molecules, Na0, Nb0. So to distinguish between this initial concentration in the reactor versus the feed, I am using CAF and CBF. Okay, so these are all feed concentrations, and they can be different. CAF and CBF can be different also. okay, and one of them can be 0, that's also fine. CBF can be 0, for example. So now we say that the K I A. So this is nothing but Q times CAF. So this is in volume per unit time. This is in molarities or number of molecules per unit volume. So you get number of molecules per unit time or moles per unit time, depending upon whether you want to use in concentration unit or number of units. So this will tell you the rate at which it is added. So when this number is multiplied by delta T, you are basically saying over a period of delta T how many molecules are actually added, what is the concentration that is added into the system. Okay, so generally we choose this delta to be very small, so that only very few number of molecules are added. Similarly, for the species B, you would write Q times CBF. And the KOA constant will be Q C CA the rate constant for the outgoing stream, that would depend on the flow rate times the concentration in the reactor. So this is a dynamically changing quantity until the system reaches steady state. So because of that, these two constants will keep changing. Okay, so these are all going to change as the system reaches steady state. Once it reaches steady state, then those constant will become those numbers will become a constant. So that's all. I mean, we have already seen, if you have a CSTR, how to apply Markov chain. The only difference for a CSTR is that these are the same. Only the reaction kinetics you have to deal with separately, depending upon what reaction is going on. Okay, otherwise it's a standard thing. So we looked at batch reactor, we looked at CSTR. You can also do PFR. In the case of PFR, you can actually use the same equation we used for batch reactor, but the only thing you have to do is what is meant as a natural time in batch reactor. If you interpret that as a space time for a plug flow reactor, you're basically going to get the same answer. So you don't need a different mathematical treatment. Okay, use the same set of equation for the batch reactor developed for applying to plug flow. Only the time has to be reinterpreted. Okay, what is natural time in batch reactor is a space time for plug flow reactor. All right. Any questions or any thoughts on this? All clear? Okay, all right. So now we'll go to the second problem of fluidized bed. So how many of you heard of fluidized bed? You've heard of fluidized one. You have also. I see you. Who have not heard of fluidized bed? Any non-chemical engineer here? It's either yes or no, right? Or maybe there's a maybe also. Who has not heard of this fluidized bed? I'm asking this because I can explain what it is. That's what I'm asking. Otherwise, I can just go ahead with the modeling part. All of you are clear about fluidized bed, what it is, right? Okay. So you basically have something like a it's a vertical reactor, and you have basically a bed of solid. Okay, these are actually granules, independent particles, and we supply gas here. Okay, so when you apply gas, the weight, the mass, the inertia of this particle will resist the flow of this gas. Okay, but if you keep on increasing the flow rate, then this bed will actually expand because the particle gets suspended. Okay, when you actually apply enough superficial velocity or enough flow rate, then this entire bed of solids will become fluidized. You get more like a liquid like behavior, all the particles colliding with each other, going up and down. You get a very chaotic fluid mechanics going on here. Okay, and the gas gets to the top and leaves, and then you might have a kind of an entry-air prevention. So you don't want the particle to be carried away from the in the gas, so you put some sort of a sieve, some sort of an entrainment trapper, so the particle do not cross this, so that you can keep this. So why we need to do this? Well, there are many gas liquid reactions that we are interested in. Okay, suppose this particle can be a catalyst or it can be a reactant, and this gas can be another reactant, and you are looking at some sort of a reaction. Okay, so it's a very kind of highly used set of reactors in the industry for gas liquid gas solid reactions. Now there are many modifications to this. For example, you can actually also add particles to the top and collect the particle at the bottom instead of having a fixed amount of solids. Okay, or you can have a this kind of a bed, and then you have a kind of a conserved number of particles in the entire system. So that is a different kind of model, and the conventional way of modeling the system would be again applying hydrodynamic theory, hydrodynamic model, and study mass transport, heat transport coupled with a reaction. You generally have something called a multi-phase flow, right? You've got a gas, you've got a solid, and then reaction between them at the interface. One does something like a CFD kind of a simulation to solve this. Okay, so now what we want to do is we want to actually kind of simulate this problem in a very simplistic manner. The idea we want to do is that if if a particle actually starts from the bottom, okay, and then it gets transported, the gas wants to push it up, whereas because of gravity the particle wants to come down. So there is a balance of two forces acting on them, right? So the gas wants to take it up at the moment because of the momentum transfer, whereas due to gravity the particle wants to come down. So there is a constant kind of interaction between these two forces, because of which the particle motion will be perturbed. So the question we want to ask is that if I insert a particle here and I want to know how long this particle actually stays in this reactor. Okay, in other words, we want to find what is the mean residence time for a particle. So generally what happens is that when the particle reaches somewhere here, it probably either is removed so that you can, so there is a different kind of operation. So when the particle comes here, you either take it out and or maybe you can reintroduce later, and so on. So there are many combinations, but what I am going to do is a very simple boundary condition. Particle enters here and then gets absorbed here. Okay, that's a very simplistic thing. And then you are asking the question, if I start a particle here, how long it takes for a particle to go from here to here? That is essentially the residence time for this particle. Okay, and you can think about a large number of particles can be introduced here, then you get a distribution of residence time, and by that we can actually get the mean residence time for this kind of reactor. Okay, so essentially we are looking at non-ideal flow in this kind of systems. So the way to model this would be very similar to our Brownian motion, where you remember we talked about asymmetric random walk, that a particle at a lattice point can go forward or backward with two different probabilities. Okay, so we can apply something similar here, because here the two forces that makes the particle go up or down, these are two different things. Okay, because of that we can think of two different probability to go forward and backward. So in the interior of the column, we can actually model this as a one-dimensional random walk problem with an asymmetric random walk, and then we have to deal with this boundary conditions. When the particle comes close to the boundary, it has to be absorbed. We talked about another problem called diffusion control reaction, or a gas molecule diffusing from a liquid and then evaporating. In those cases we talked about boundary conditions. We are going to apply something similar here also. So as you can see, the principle is very same: diffusion plus boundary conditions, diffusion plus some sort of managing the inlet, outlet and boundary condition. Otherwise the framework is very similar. You can apply wherever you want: CSTR, PFR, packed bed reactor and so on, so fluidized bed reactor and so on. So okay, so what we can do here is we will make this as a one-dimensional problem. right? So we have what we will do here is this entire column we will break into cells, okay, some horizontal cells of some finite thickness like this. So this entire column is broken into some n number of horizontal cells. So we say this is cell number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and so on. So in fact we will say this as n plus 1. Now when we talked about the one dimensional asymmetric random walk, we had an infinite lattice both ways going back minus infinity to plus infinity, but here we have a set boundary condition. So the particle can only be injected here and it can be absorbed there. Everywhere in between it is going to be an asymmetric random walk problem. Okay, so here we are going to set up Markov chain. Here the Markov chain means that the particle can be found in any one of these cells. So it got a finite number of sets. Remember, if you recall, we apply Markov chain model whenever the number of states are finite. Okay, here we have a finite number of cells. It's often a question for us to understand, if I have a physical dimension, how many cells I need to do. Okay, so generally people actually do this over many different kind of cells and then see some sort of convergence. You should have adequate number of cells to capture this random motion here. So let's say we have found n and n has to be optimized later on. What this n should be? Can I have just only two of the 2 cells or 3 cells, or should I have hundreds of cells, thousands of cells? We don't know. So that has to be optimized later on. So how do we do this? So we wanted to basically we are basically thinking about a transition matrix, something like this. It's going to be a n plus 1 by n plus 1. Okay, you have cell 1, 2, 3 all the way up to n plus 1. Similarly, cell 1, 2, 3 all the way up to n plus 1. So the dimension of this transition matrix is going to be n plus 1 times n plus 1. Okay, what that means is when I am state 1, I can remain in state 1, or I can jump to 2 or jump to 3, jump to 4, jump to 5. Okay, so that's what all this transition property means. Okay. So we'll come to boundary condition later. Let's say you are at cell 2. Okay, so I got a particle. I'm actually having a particle somewhere here. What this particle can do is it can actually jump up, or it can actually jump down. So this rate, so I have got state 2. From state 2, it can go to state 1 or it can go to state 3. Okay, so those are the two probabilities. So from 2 to 1, that would be going down, and we will consider that as alpha. Okay, the probability for it to jump down is alpha. It is because of gravitational force. And then the probability it can actually go from 2 to 3 is a upward jump. I will do this as beta. Okay. Now I am writing everything in terms of probability per unit time. Now the probability that it will remain in the same state would be simply 1 minus alpha minus beta. Can it jump to state 4, 5, 6? It doesn't jump too far. It's only making an incremental jump to the next neighboring cells. So all the other elements are going to be 0 all the way up to n plus 1. This is a fate of a particle being in the cell 2. Now let us say I put the same particle in somewhere in cell 3. So here in this case in cell 3 you have alpha here, beta here, 1 minus alpha minus beta, right? Everything else is going to be 0. Right? So you can see it's nothing but an asymmetric random walk over the cell. Similarly, when I go to 4th cell, it will be 0, 0, alpha 1 minus alpha minus beta and 0, sorry, beta, and then 0, 0, 0, like this. So you would actually do this all the way up to cell n. Okay, so this is cell n. When you have a particle at cell n, of course it can come down, it can remain here, or it can jump to n plus 1. Now what is important is what is happening at n plus 1, that is important. When it comes to n plus, so at the cell n plus 1, this can, once it reaches here, it is actually taken out, it is actually it's a dead state. Okay, so you have a possibility of only going from n to n plus 1, and nothing from here onwards, it cannot go anywhere else. From n plus 1, it doesn't go anywhere else. So from n plus 1, so you have to make all of them 0. So let me also put n plus 1 here and n here. So all of them will be actually 0, 0, 0, and the last one will be just 1. If it is an n plus 1, it is going to be n plus 1, it is not going to come back. Whereas when it is n, it can remain in n, or it can actually go to forward jump is beta, something like this, and everything else is 0. So when it is n, it can jump forward to n plus 1 or remain in n, that is these two. When it reaches n plus 1, yeah, it can come down to n minus 1, that is true. Okay, yeah, yeah, that is right. So we will put that as alpha here, like this, yeah. So when it is at n, it can go up, it can come down, or it can remain so. When it is at n plus 1, it's not going to come down. Okay, it is like a dead state, it's not going to come down, it can only remain there, it's like an absorbing state. So that's why I put 1 here. What about state 1? Okay, so here this is where we are going to introduce, okay, because this is like a reservoir, this is where the particle begins. So it cannot actually go down, and it can remain in 1, or it can go upward. So it's going to be beta and 1 minus beta, and the remaining are 0. So you introduce at 1, it can jump or it need not jump, that's all. So yeah, yeah. Like I said, there are many modification of this model about how you want to introduce, how do you want to manage the boundary conditions, whether you want to have a constant inflow or you have more like a reservoir, and and so here what we are saying is we are actually introducing only one particle, and when we are asked, so this transition matrix will tell you where you will find this. If I create one trajectory starting from here, okay, you will see which cell the particle is actually going over time. So when you update the particle position over time, you will see that it remains in cell 1, in second time interval also stays in point 1, and then later on it kind of goes. So, you will get a trajectory when you solve this, and let us say this is your cell index. Okay. So, you would have started at cell 1, okay, and the particle probably remains over a period of time in here and then makes a jump to 2 and maybe stays there for some and then come to 1, and then it stays for some time and then go to 2 and then stays and then goes 3 and so on. So this trajectory is a fate of one particle introduced at origin according to this model. Now when you create many such trajectories, you will find at what time the particle reaches n plus 1 state. That would be its residence time. Now when you create many such trajectory, you will see one trajectory ends at time 10, another trajectory ends at time 5, another trajectory ends at time t equal to 100. So you will get a distribution of time, absorption time at the bottom, at the top, and when you get a histogram of that, you get a mean residence time, or you get a distribution of residence time. Okay, so that's the use or the utility of this particular model. Okay. Now, if you want to add more modification, like he said, if you want to constantly introduce particle from the inlet, you can do that with some flow velocity. Consider this an inlet condition. Another modification people do in this problem is that here we are talking about individual particles moving up and down like a asymmetric random walk. In reality, sometimes the particles are captured in a gas bubble and immediately reaches to the top. Okay, from any cell I, the particle can be taken to the top of the cell and leave the system. Okay, so that is called again entrainment. And if you want to model that, you are going to add one more term in the last column. When I am cell 3, I have certain probability that it will go directly to the top of the column. So you can actually have another constant here if you like, put gamma something like this. Okay, and you have here gamma. And this can be applied for all the other cells also. So like I said, there are many modifications. The base model is this, and what are the sophistication you want to add to it, what are the additional feature you want to add to it, you can do this. Okay. So like I said, if you operate this transition probability, and of course you have to set what is alpha, what is beta. If you put alpha and beta equal, then you are talking about a random motion, random walk, Brownian random walk. And if you put asymmetrically, you know that so this is where our job is. We have to find this alpha and beta by doing some physics-based modeling, that how much force is acting on a particle and over a period of time, delta time, how much is going to come down, how much is going to go up, all that you have to deal with. Okay, so I'll just stop here, and tomorrow Friday when you come with your laptop and try to do this problem and the CSTR problem. We'll give some numerical example, and you'll have to code and then make trajectories, get statistical properties, and do some exercise. All right.